Hello. Welcome to Statistical Methods Summer Term Part 2. The topic of the second half is variational inference. Hello, can we start, or what's going on? So variational inference is a general purpose method for doing model inference or model estimation and model evaluation for all sorts of quantitative models in a scientific setting. That means if you want to quantify uncertainty, because as you know, nothing is really certain, and specifically in science you can only be so much certain in the theory that you posit to explain certain data. And variational inference it's kind of like a hammer that you can use whenever you want to quantify your uncertainty, do probabilistic inference, or as some people say, do statistics on some kind of model. And of course the model that we have primarily in mind right now is DCM5MI, because that's what we talked about the last 5 weeks. And as it turns out, of course, variational inference, or variational Bayes as it's also sometimes called, is the method that is used by your favorite toolbox, namely SPM, to estimate and evaluate dynamic causal models. So to introduce variational inference, we have to again take a little bit of a tour through probabilistic inference. And as I asked you last time, I hope you all brushed up your basic probabilistic skills, so that you watch the basic probability mass function, conditional probability mass function business that we provided as online lectures and also in the handout, and also that you looked into Gaussian distributions a bit, because as we will also see over the coming weeks, variational inference is mainly put to practice actually in parametric models, meaning in statistical or probabilistic models that use parametric distributions that usually are specified in terms of probability density functions and their parameters. So I hope you are up to speed with these things. And then based on these basic probabilistic modeling aspects, we now build and provide an introduction to variational inference. And we start today with some motivation. So why do we talk about variational inference at all? And then with basically the starting point of variational inference, namely Bayesian inference. So I will often say variational inference or variational Bayes. I mean the same thing if one really wants. So one can, of course, define variational inference as being something different from variational Bayes, but for what we do, it doesn't really matter. And the other thing is that in the end, the question is, what are the random variables you're inferring about? And then whether you call it variational Bayes or variational inference, I really don't care. So I think variational inference, the term is a little bit nicer in the sense that it's not so closely connotated with Bayesian inference, where so variational Bayes, so variational inference versus variational Bayes, because Bayesian inference versus classical statistics also has a certain meaning, and we might actually talk about a little bit about that today. And the focus on Bayes is not necessarily helpful. The whole thing is probabilistic inference, and one way to do probabilistic inference is variational inference. And the term Bayes in there, we will talk a little bit about what it means. So today, that's what we want to do. So mainly focusing on motivation and getting started with Bayesian/probabilistic inference. Then next time we want to talk about multivariate Gaussian inference, variate Gaussian inference. So there it's not only talking about how multivariate Gaussian look like, but specifically these joint multivariate Gaussian marginal and conditional Gaussian distributions. So if you looked into the Gaussian distributions for today, you might have seen these already because they are the later part of the Gaussian distributions, but we will talk about them, so the later parts a little bit more in detail, maybe also looking into some proofs there. Then, based on this, we will talk about Bayesian inference for the GLM, because what I want to establish specifically with these two cases here is the normal case, normal in the sense not of Gaussian, but in the sense of not unnormal, the normal case where you don't need variational inference. But if you've never seen the normal case where you don't need variational inference, the motivation for variational inference is also not quite clear, and its boundaries in terms of if you use certain forms for the variational distribution that then correspond to the normal or the standard case. Let's call it standard, it's maybe less confusing. Then it's not quite clear what variational inference is about. Then we will talk about the foundations of variational inference, which are a couple of integral equalities, fairly straightforward. Then we will look into the name, essentially. So why is it called variational inference? Variational. And this has nothing to do with variance, so don't confuse that. It has to do with what we then briefly will talk about, namely variational calculus, which is kind of the next step after standard calculus. You would usually do variational calculus. And once we have established these things, we are then in the position to look at free-form mean field variational base, which is kind of a textbook approach to variational base. So it's kind of a simple example where you can show certain aspects of variational base, but it's not something that you will often then actually use in practice. What you often use in practice are specifically if you do DCM for fMRI, what you often then use is what is called fixed form mean field variational base or variational inference. Like I said, I'm using both things kind of interchangeably, and we will do this for definitely 2 sessions. And this here you can also view from the perspective of the summer term as DCM for fMRI estimation. So remember that we discussed the formulation of dynamic causal models for fMRI so far, but we haven't discussed at all how the parameters are estimated. And they are estimated using fixed form mean field variational inference. And to explain how that works, we have to do these first 6 sessions, and then we can discuss how DCMs for fMRI are estimated, namely using fixed form mean field variational inference. And then we are also done with DCM for fMRI. Yeah, so you can view this second part of the summer term in 2 ways. You can either think about it, okay, we learned about DCM for fMRI, how it models observed bold data, and we looked at it from a computational neuroscience perspective. So we formulated a model and simulated some data, but we didn't use this to actually infer parameters of the model from data. And now in the second half, we actually learn how we can bring our model together with the data and inform the model by the data. So you can view it as this, or you view it as a course in Bayesian and variational inference that is kind of a general purpose method that you can always use for probabilistic models. And as a specific example of that, we look at DCM5 Yeah. So either way is fine. Of course, the second viewpoint is a little bit more general. Okay. Questions about this. So this is essentially also giving you a guideline of what to read from the script for the session, so that you are prepared and you know what's going on. So if you pointed out the sections in the script last time, and yeah, if you of course, I think the biggest chapter where most of the material is found is the variational inference chapter. I think everything from 4 to 8 is in there. Yeah, so that you know what will happen and that you can prepare. Questions about this right now? No. Good, then let's start right away with motivation and Bayesian inference. So today's session. Motivation and Bayesian inference. And the question is, why do we talk about variational inference? And why should you, as an aspiring cognitive neuroscientist, be interested in variational inference? There I want to give you some motivation, because I can also imagine that it sounds a little bit outlandish for you. So who has heard, except the people that I talked about the free energy principle with, who has heard about variational inference in some other context than me talking about it? Yeah, so that's in a way that's what I expect. So it might sound a little bit outlandish and something that's not on your horizon, and that's okay. So what I'm trying to do is give you some motivation, and the reason why you haven't heard about it, it's because it's in a way, it's fairly advanced and it's fairly contemporary. Yeah. So when you talk about t-tests and undergraduate statistics, when was t-test invented? Roughly 100 years ago, exactly. And variational inference and variational Bayes were invented. It's always hard to say when things were exactly invented, but they rose to prominence, let's say, in the 90s and early 2000s. And then they took a little bit of a dive in around 2010, when neural networks rose to prominence again after they had been out of favor for quite some time. And then variational inference together with neural networks came back, and actually now is a current theme. So so this stuff is definitely not stuff that you find in psychology undergraduate statistics textbooks, because it's modern stuff. It's actually research-oriented teaching that I'm doing here. Yeah, so it's current stuff that people today are interested in and work on. So and now so that as an explanation why you haven't heard about it, the first and I think biggest motivation to look into variational inference is, as I already said, it's a general purpose method for probabilistic inference. Purpose method, or as I also call it, for probabilistic, and for me probabilistic inference and scientific inference are the same thing. Probabilistic / scientific inference. And that's the core motivation why I am for probabilistic scientific inference. Sorry, why I remain to be very interested in variational inference, variational-based methods, because it's something that it's a tool. It's an intellectual tool that you can use to do scientific inference. And why do you need this tool? As a scientist, well, you are interested in developing quantitative theories and testing them based on data. So you need somehow a link from the data world to the model world and back. And variational inference provides this link in a very general setting and in a very in a theory-based and in the end in a very beautiful manner. That's the main motivation. However, to really get that, of course, you first need to know what variational inference is. So this kind of motivation, I hope it develops over the next 8 sessions so that you see that. But I can give you easier motivations to look into that, which I will do now. So from what you've seen so far in this course, it's the thing that can be used for estimating DCMs, and I decided I would prove everything to you today because it's on the internet, which is of course a very strong proof, because everything that is on the internet is right. So this is the Wikipedia entry for dynamic causal modeling, and you see certain things that we also discussed, so things like that, for example, which we've seen. And then if you go to model estimation, you will see model measurement using variational base and the Laplace assumption, which is, yeah, that's a wrong link in Wikipedia. This is something that I think leads you to variational base in Wikipedia, which you can also look into. Yeah, so if you deal with DCM, the big thing is that it's estimated using variational base, as Wikipedia proves. The next motivation that I can give you for this is if you are into this distinction between Bayesian and frequentist inference. So does anyone of you know or can say something about this? Bayesian versus frequentist inference? So does it ring a bell at all? Yeah, so.
Kind of reason that like frequentists always have some parameters that they have to assume, so they always like the wrong distribution. It's not true.
Well, there's something to it. It's not wrong. Did in undergrad statistics in your courses never came up that what you learned there is frequentist statistics, and then there's this world called Bayesian statistics? Did that never come up?
It came up, but that's about it.
Oh, that's about it. Okay. Yeah. So I mean, definitely what we discussed in also when we discussed the GLM is the frequentist viewpoint, where you basically don't model parameters based on random variables, which is the Bayesian framework, and which we will look at a little bit today, so that gets clear. The main thing, or one aspect of Bayesian versus frequentist statistics is the interpretation of probabilities. Hello. the Bayesian viewpoint is more related to, let's do it like this. This is more related to quantifying subjective uncertainty, although there's also something called objective Bayes. But generally it's more about specifying or talking about probabilities, like the probability that Daenerys will die today on Game of Thrones is something. I watched the first 10-15 minutes. She's not dead yet, so I can update my probability for that, but it's also not looking better. So it's so from 50-50, I'm maybe at 60-40 right now after like 10 or 15 minutes. That's a mild spoiler. You didn't expect she dies in the first scene, right? Actually, somebody else dies after 15 minutes. So that's the Bayesian way to talk. Sorry, that's the Bayesian way to talk about frequentist. The Bayesian way to talk about probabilistic concepts. The frequentist manner is more in terms of large sample limits. Yeah. So this is also. I mean, you can also do it with this Game of Thrones example or whatever you like. Talking about the probability that one of the characters dies in episode 7 of 8 of Game of Thrones in the 8th season, you can talk about this probability, but you cannot talk about it in the sense of a large sample limit, right? Because that would mean that Benioff and Weiss would have to make like the 8th seasons many times. And from averaging over that, and when characters die, you would then be able to talk about a probability. And clearly, this is not what people have in mind when they talk about probabilities in these kind of settings. Yeah. However, that's where the frequentist approach is definitely rests a lot on. And you remember that from the winter term when we talked about the GLM and that we sample from it. And if you sample many times from it, you get many samples. You can compute many beta parameters, and then you get these empirical or frequentist distributions of parameters, which then also lead to the t-distribution, if you also take into account the variance parameter estimate distributions. So that's kind of the frequentist viewpoint. Now, why is variational inference then has something to say with respect to that, and why is it important right now? Because, as you know, frequentist statistics, specifically talking about p-values, is again and again exposed to some criticism, and there I just want to put these links into a Word document so you can also look them up. If you haven't seen this yet, there's a very nice current issue of the American statistician that has a lot of articles that essentially go or want to go beyond making statistical decisions based on p-values, so the classical frequentist scenario. So there are just many articles, and some of them then also feature Bayesian methods. So, for example, here p-values, Bayes vectors, and sufficiencies, and so on. So that's one aspect. So I don't want to make this aspect too big, because it's definitely not the case that you should take from it that Bayesian inference is the solution and frequentist statistics is all wrong. One can do Bayesian inference. It's still a probabilistic model, and the interpretations, and there's still interpretations to the stuff that one gets out. So one also needs to know about this. It's not just like the better thing, although it's definitely more intuitive, and there are good mathematical reasons to perform Bayesian inference, not frequentist inference. But it's one aspect of this, and we might get back to that when we talk about things in more detail. So then maybe a little bit of a more, if you are a little bit, I don't know how woke you are, but if you are woke, then you will have realized that currently a lot of people talk about artificial intelligence, and that there are things like Facebook and Google and things. And variational inference is a topic in current artificial intelligence and machine learning. So it is a topic, and to prove that, here, this, for example, is the deep learning textbook from 2016, which is one of the textbooks in machine learning. There are better textbooks in machine learning, for example, the Murphy book from 2014, or the Barber book from 2012, or even the Bishop book from 2006. The deep learning book is basically was written based on this recent hype in neural networks, which of course have been around forever and also feature in all other machine learning books that came before this. But if there's a hype and there's a new word that means the same things as everything before, people start to get interested. And so this deep learning book talks a lot about neural networks, of course, because that's after all, deep learning just means learning neural networks with more than one layer. Yeah, so always keep that in mind. So it talks about these things, but then if you go a little bit further, so you pass the first chapters on neural networks, and in the end, you end up in approximate inference, where the probabilistic viewpoint is reintroduced. The big problem that I have with neural networks is that, neural networks are fine. They can be used to approximate arbitrary functions. That's also nice, although it's not that interesting from a scientific perspective, because we don't want to build arbitrary functions to explain data, but we want to come up with functions that have some biological, cognitive, or whatever kind of scientific connotations, and not just arbitrary concatenations of linear and nonlinear transformations. That's one aspect that makes neural networks uninteresting from a scientific viewpoint. The other aspect that makes neural networks not that interesting from a scientific viewpoint is that they don't quantify uncertainty, because they are not probabilistic models. However, if you are interested in quantifying uncertainty, which is the next step once you actually came to the realization that scientific theories are quantitative models / functions, then you want to quantify uncertainty. And hence, in chapter 19, they also come to that conclusion and start to quantifying uncertainty. And then, if you work a little bit into that, at one point you end up at variational inference. Yeah. So this shows a little bit that variational inference is, of course, not the first thing that you see in a book that you open on contemporary machine learning, but the reason for that is that contemporary machine learning was on a good way in the from 2000 to 2010, because people started to think probabilistically. But then maybe things got too complicated or so, and then people thought, I don't understand anymore. Let's just do neural networks again, and then they did neural networks. But it's the variational inference paradigm is still there. It's a little bit advanced. The good thing is, and this is what, if you look, for example, in what people talk about at NIPS, which is one of these artificial intelligence machine learning conference, or ICML, which is another one, so the International Conference on Machine Learning, or the Conference on Neural Information Processing System. What people talk about there is variational inference. So, for example, under the new name of variational autoencoder. The good thing is, in 2014 there was a paper by Kingma and somebody else at NIPS that introduced this term variational autoencoder. What they mean by that is variational inference. And somewhere in variational inference, you put at one location, you put a neural network, and people then thought, well, that's very new, so they also jump on that. And so what is the case is definitely that variational network inference variational autoencoders, ELBO, which is the evidence lower bound, which is a central quantity in variational Bayes. These are all current topics in machine learning and artificial intelligence. Yeah, they are all. If you talk about artificial intelligence, and I think the next thing will actually show that variational inference. They are all statistical learning techniques. If you talk to me about artificial intelligence, that's not the only thing that you need for artificial intelligence, because speech recognition. For me, that's a statistical inference problem. It's not artificial intelligence. Artificial intelligence, from my perspective, needs to act as well. And if you're interested in artificial intelligence, then you need, in addition to variational inference, you need things like partially observable Markov decision processes and the way that they can be addressed. So also to link variational inference closer to artificial intelligence. So there are these nice lecture series by DeepMind, which you can also find on YouTube. So they did a course at UCL, I think, UCL in 2018 to recruit more people for their company, I think, I guess. And if you go a little bit further down here, so there's I haven't actually watched these lectures on reinforcement learning. I watched bits and pieces of it. It looked a little bit superficial, but maybe it's okay-ish. So if you go, there's a lot of deep learning, meaning neural networks in the beginning, where they actually are state of the art, and it's very nice. But it's neural networks after all. Later on, here in this lecture, this guy, what's his name? I don't know what his name is, but he talks about variational inference, generative models, and basically what we will talk about. Yeah. So the thing is, in machine learning, they are not that interested in inference and prescribed probabilistic models. In machine learning here, variational, yeah? So that's the main point of this thing that I'm doing right now. The thing with machine learning and AI is that they don't really care about the models that they apply these things to, yeah, because they are mainly interested in having good prediction, and the model can be whatever. They don't care about the model as long as it gives good results. We, as cognitive neuroscience, we obviously care about the model because it's our scientific theory of how the brain works, how people behave, and how this relates to a brain function. So we look at variational inference a little bit different, which leads me to the last point. So let me complete this here. So this was the machine learning AI pep talk. And then one last reason to talk about variational inference, specifically in the context of cognitive neuroscience, is the infamous free energy principle. That's the free energy principle is from my perspective, the first general theory about brain function, started around 2005 by Carl Friston, who interacted with Geoffrey Hinton, who was one of these machine learning godfathers, who was at Gatsby at that time. So they talked a bit, and then Carl Friston in 2005 decided. Carl Friston, 2005, decided brain does variational inference, or at least that's what he decided to be the theory, and that's the free energy principle. So that the brain does variational inference or variational Bayes, and since then they have been he has been developing this idea, and looked into its ramifications for both perception and for action, where it's then called active inference. And the idea is that variational inference is used to solve partially observable Markov decision processes or their continuous counterparts. That's the free energy principle. It is quite mystic, and things like, do we get it? Oops, no, we don't want to sign. No, thanks. Go away! Don't lose the future. Oops, now we're getting to some strange things. Hello. Let's try that again. It's so mystic that we can't even look at it. So it's very mystic, and this is the genius neuroscientist who might hold the key to true AI. And actually, you see the light of God going there. It's fairly mystic. The whole thing starts with King George of England. I don't know what it has to do with King George of England, but anyway, the article is actually quite nice. So I don't want to make fun of this article. It's a nice article actually, which I somehow can't navigate. But go away. So it's a nice article. It describes background to this. The only problem with this and the whole rhetoric about the free energy principle in cognitive neuroscience is that it's treated it's treated like first, yeah, this is what I the first point, the free energy principle is maddeningly difficult to understand. It's treated like this great idea that is very important and everything is important, but nobody can understand it. Only Carl Friston can understand it. So that's completely not true. The first thing is that variational inference can be understood. The other thing is that what cannot be understood about the free energy principle are the things that are not worked out in the free energy principle yet. So it's a theoretical framework that develops, and certain things are understood. It's a theory, and certain things are understood a little bit more. Other things are not formulated and talked and created yet, and then there is also nothing to understand yet. So it's not that that there is like that the free energy principle is like in this book and there's the solution and nobody can understand this book. The free energy principle is just not fully developed, and active inference is not fully developed. So stories from the future, exactly. So, yeah, one can understand the free energy principle as far as it is developed, because this is variational base and the interpretation of variational base in terms of cognitive and neural function. What one cannot understand about the free energy principle is what is not formulated and spelled out yet. Yeah. So, and the other thing that you always also need to keep in mind with free energy principle and active inference is it's a model, it's a theory, and there is hardly any empirical support for any of that. Yeah, so it's just a theory. It's a thought experiment. Yeah, and so somebody thinks, okay, let's say the brain does variational inference. What does that mean? Let's think about it and let's write about it. That's it. Yeah. Good. So that was kind of the last motivation that I could think of this morning for talking about variational inference. Good. Questions about these motivations at this point? So while we talk about variational inference, or any aspects that of these motivations that you are not quite clear about yet? I mean, of course you don't know what variational inference is yet, but maybe you have some specific questions.
Sometimes you also see that people use sampling, right? Stan and stuff like that.
MCMC.
Yes. So we talk about deep learning, but is that actually a thing that you either do this or that? Or
so there are, in a way, you can view the whole thing of approximate probabilistic inference, and variational inference is a form of approximate probabilistic inference. You can view it as there are two ways you can do that. You can either use variational techniques, or you can use sampling techniques. And then there's also current work that actually tries to combine them. So, for example, stochastic or black box variational inference uses sampling techniques to approximate certain integrals in variational inference, but does variational inference overall. So it's not either or. From my perspective, variational inference is kind of what you do if you want to do probabilistic inference, but your model got a little bit too complicated that you can solve all the integrals in there. MCMC is the same thing, but uses a sampling technique, and in its most basic form uses a random number generator to estimate probabilistic aspects of your model. And basically, and from my perspective, this is where MCMC is weird if one looks at it like that, because you create something mathematically intellectual, and then you think about how can I now combine this with data, and then variational inference gives you a way to combine this with data by thinking further and optimizing certain things. Maybe numerically, but you optimize things. And MCMC tells you, well, you have to turn on the random number generator, or you actually have to throw a lot of coins. And that's where I think MCMC is weird. So if this whole thing is a modeling exercise, why do I at one point need to turn on a random number generator? So that's weird. However, if one goes more into the details, MCMC and variational inference are different ways to approximate integrals. So of course there are toolboxes for MCMC. There are actually also toolboxes for variational Bayes. I think variational, that's one thing. The other thing is that MCMC is just something about sampling. If you use this for posterior distribution inference, you get sampling distributions, you get histograms, and then you have to make some sense of them. And then you can approximate your posterior distribution based on histograms that you observed in your random sampling. And then you also don't have an approximation for the evidence, all of which is nicely integrated in variational inference. So MCMC and sampling methods are just random collections of things that you can, but they are not a nice, intellectual, beautiful framework. So that's why I'm not a MCMC person, a variational inference person. Although, of course, if you go deep into variational inference, then you also get into numeric questions, and then there are different ways to answer these numerical questions. And one answer is also using stochastic optimization, using sampling. But that's, of course, you can only understand that really if you really understand what variational inference is, and if you really know how MCMC is being used. So, and nothing is wrong. Some things are just nice, and other things are not that nice. Any other questions? No. Good. Then let's have a break and continue at 9 with first introduction to Bayesian inference.